This is 13.3 wave functions. Today we're going to talk about how to write oscillation functions for position, velocity, and acceleration. Mostly, you're going to memorize the three equations, and then I'm going to teach you how to pick them apart, the information out of them. And they look kind of scary, but once you know how to read them, they won't be that hard. If you've done sine and cosine equations in pre-calc, I think it is, where you've learned about the amplitude and the frequency, this is the same sort of thing. We're just applying it to simple harmonic oscillators, which, remember, are just things that go back and forth at the same rate. And they have a restoring force. So circular motion and simple harmonic motion. You can think of circular motion kind of like simple harmonic motion because they're both periodic. Circular motion does not have a restoring force, which is why it's not a simple harmonic oscillator. So the Earth going around the sun is periodic, and circular, well, mostly circular, but it is not simple harmonic. But we can relate the two things together. So we can talk about things having a period in simple harmonic motion, things that have angular frequency, if you want. So you're converting frequency to angular frequency. And remember, simple harmonic motion is SPHM. That's just talking about the back and forth motion, and a simple harmonic oscillator is talking about the object itself. So basically things that go back and forth. They're big scary words, but they really do not mean anything. You see one red cup? Here are some equations for you. I thought I'd just write them all down. We have velocity. I believe this is the velocity at the equilibrium point. And that is, so like maximum velocity. 2 pi amplitude over the period. So you have 2 pi, this is kind of like r, right? 2 pi r, like a whole circle, except for we're translating it into some harmonic oscillators. So that'd be like its maximum distance away from equilibrium. So that's going to be in meters, because usually your amplitude is either in centimeters or meters. Make sure you put it into meters. And then the period, the amount of time it takes to go from one spot to that same spot. So that's your time per second, so meters per second.
So wait, this is for like a pendulum?
Pendulum or a spring, or anything that they just say simple harmonic oscillator. There's a couple of things that they are like, I mean, a swing is basically a pendulum.
Yeah.
We'll talk about that. They could say a particle with simple harmonic motion. And I'm going to talk about the right side in a second. We'll just talk about this. This is kind of more circular motion translated to simple harmonic motion. Your angular frequency is 2 pi f. Remember, f is cycles per second, or hertz. And then period is the inverse of frequency. It's going to be 2 pi maximum amplitude over your velocity, which is basically this equation just switched around a little bit. Again, this will be your, I believe, initial velocity. Can't be maximum. I think it's velocity at that point. All right, on the right side here, this works for springs. So mostly, you can use this for springs if you're talking about it without talking about the K constant. This is more like what you're going to see in your equations. This one works pretty much for springs because you got that K constant in there. You've got your maximum amplitude, your spring constant, and your mass. Your angular frequency is just your square root of K over M, and then your period is 2 pi M over K. You guys remember gravitation? Mm-hmm. Did we do the equation for a pendulum for this stuff? Maybe. Okay. Because the equation for a pendulum period is 2 pi L over G. And there
I remember writing it down, but I don't ever remember using it.
Okay.
What's the left side for you?
The left side, this is what you're going to see more in your equations, and I'll show you the equations in a second. And this one's more specifically geared towards things that have spring constant. But this one can be used for springs if they're not talking about the K constant. This is like general simple harmonic oscillators in circular motion, and this is specific for springs. So it's kind of like this is equal to this, if you want to translate that. I would definitely recommend writing these equations down. I think they include them on the AP exam, but I think they might be like worded strange or convoluted. Like they're not as simple as this. They're going to give you like 3 of these equations where I've just given you 6. So you'd have to like translate more of them. So I'd write them down. Okay, you guys ready for the scary equations?
Yeah.
Okay. I see one red cup. That's why I'm asking. Okay. Wave functions. These are the 3 scary equations. This is the position equation for anything in simple harmonic motion. So, period. Spring, pendulum, particle in simple harmonic motion. This is the velocity, and this is the acceleration. The velocity is the derivative of position, and the acceleration is the derivative of velocity. So you can see that the inside stays the same. And then here you've got your omega, which is basically 2 pi frequency, right? So that comes out, and then they do it again, and that comes out, and you go from cosine to negative sine, and then back to cosine.
That's frequency and that's time.
Frequency and time, not period here. Period would be capital T.
Another question. It does not get worse.
This is like the most complicated stuff that we'll do. This is the nasty stuff, which is why I'm saying just memorize it.
Wait, really? This is it?
This is, this stuff's scary. I know this stuff.
Wait, this will be the hardest stuff we will be doing this year.
I'm not going to promise you anything. I'll just break my promises.
Okay, but this is one of them.
This is a difficult thing right here.
Okay.
He's asking for something harder.
Oh.
No.
Yeah, that's what I'm asking for.
I was trying to run but now you guys are going too far.
Yeah, sure. Okay.
We got it.
Happen now.
Now, for these functions, because we're doing 2 pi frequency, you need to make sure that your calculator's in radians. This is the only part of physics that you need to make sure that it's in radians. All our stuff we do in degrees, except for these 3 equations. And that's because it's got this weird 2 pi thing going on. Now this 2 pi frequency can be translated into omega, right? 2 pi f. So this can be simplified to a cosine omega t, negative a omega sine omega t. So you use what you need to.
Only these 3 are including the last one.
Only these 3 do you need to be in radians. If it's radians or not, it doesn't matter because you're not using trig functions. So you can substitute to get all the numbers for this thing. You can use these equations to simplify them. So if you're given k and m and you need omega, you can take your spring, do k over m, square root of k over m, and then plug it in here for this 2 pi f, which is omega. So these equations are supposed to support these equations. I see blue cups. Anybody want my time? Okay. So let's look at the graphical representations. Again, you do this a lot in, I think, pre-calc is when they do this stuff, where they're showing you sine and cosine waves. There is some phase shifting stuff, which I'll talk about a little bit, but I don't think they're going to throw too much of that of these at you. It's kind of nasty. So when x is at a maximum or a minimum, the velocity is going to be 0. So here's your position. It's saying that your equation is a cosine omega t. So whenever your x is equal to a, right, it's at the furthest stretched point or the highest point on that pendulum, it's going to be a 0 velocity. So you can see that here, when x is at a, on your velocity equation, you've got 0. And you can see that the acceleration is going to be in the opposite direction which you pulled it, because of Hooke's law, F equals kx, negative kx, where this is going to be ma equals negative kx. So here they're saying when x is maxed, or equal to the amplitude, velocity is 0, And your A is going to be at a max, but in the opposite direction. And that's because MA is equal to negative AX. So if you draw a picture of this, again, I'm big on pictures here. When X equals A, so right here, this is its maximum amplitude. Your X, let's say this is a positive X, your acceleration or your force is going to be that direction, pushing it back towards the equilibrium point because it wants to go back to where it was. And its velocity is going to be equal to 0. So let's look at it when it's at the equilibrium point right here. Here, V is max, X is 0, and A is 0. Because it's already at this point. It has no restoring force when it's at equilibrium. And it's at equilibrium, so it has no X. So if we look at our graphs here, when X is equal to 0, you should have a maximum velocity and a 0 acceleration. So you can double check these things. Make sure they work. Or you can draw a picture, or you can do the math. I'm just going to look at one thing first. Okay, 6 questions. So that's not too bad, right? That's pretty much all we're learning today. You okay with that? These are kind of scary. All right, you guys ready for your questions? One more time to look at these pretty graphs. Yeah. Okay, switch your cup for me. Thanks.